Hello, my name is Howard Wilson and I am Professor of Plasma Physics at the University of York and have recently returned from a secondment to UK Atomic Energy Authority, where my roles included the Interim Director of the £222 million STEP fusion reactor design programme. I am going to tell you a bit more about the status of fusion, focusing in particular on the tokamak. This is a fusion energy device which holds the hot fusion fuel in plasma state, keeping it away from the walls by a toroidal configuration of magnetic field. The international fusion community is presently constructing the ITER tokamak in the south of France, which is the biggest international science project on Earth. Designed to deliver 10 times more fusion power than the power injected into the plasma to reach fusion conditions, it will answer the remaining science questions and address much of the technology required to build the first demonstration power plant. This is an exciting prospect that is at the culmination of decades of research. The progress to ITER can be illustrated with this figure. Along the x-axis, we plot the temperature. The centre of the Sun is here at 10 million Kelvin. Up the y-axis, we plot the triple product, the product of the plasma density, its temperature, and something called the confinement time, which measures how good the magnetic field is at containing the plasma. The curves labelled Q equals 1, which is where fusion power equals the plasma heating power injected, and ignition indicate the values of temperature and triple products required for commercially viable fusion power plants. Our story begins with the small Russian tokamak T3 back in the 1960s. A team of British scientists travelled to Moscow to make the first measurements of temperature in a tokamak plasma using a new laser-based system called Thomson scattering. These measurements showed the huge potential of the tokamak, but T3 was still a factor of 100 too low in temperature and a factor of 10,000 off in triple product compared to where a commercial fusion reactor must operate. Nevertheless, excitement about the very high temperatures achieved led a number of tokamaks to be built outside the Soviet Union during the 1970s and 80s, achieving still higher plasma temperatures and higher triple product. These acronyms are the names of different tokamaks. You can see how rapid progress was made through the 1980s, especially with the operation of the European tokamak JET in the UK, which is still the world's most advanced fusion facility. During the 1990s, both JET and the Japanese tokamak JT60U finally demonstrated that Q equals 1, scientific break-even, is possible. To go further with this kind of tokamak design required a still bigger device to achieve the necessary triple product, and that led to the design and construction of ITER. JET underwent a huge programme of work to replace all its internal tiles to be of the same materials as planned for ITER, beryllium and tungsten. This was all done with state-of-the-art robotic systems, again a key fusion technology. If ITER is successful, and there is much scientific evidence to indicate that it will be, we will need to push on towards the design of the first demonstration fusion power plant. Several countries are thinking seriously about this. In Europe, the focus is on a demonstration power plant that is a scaled-up version of ITER. The strategy is to build an irradiation facility called IFMIF donors that will test materials in a fusion neutron environment and will operate alongside ITER and, in parallel, design the demonstration power plant called DEMO that will likely operate from the 2060s. The UK is a strong partner in this European programme, but with the urgency of climate change, is asking the question, can we deliver fusion faster and with lower capital cost? This is the goal of the STEP programme, the spherical tokamak for energy production. Specifically, STEP is assessing the feasibility of delivering a prototype commercial reactor by 2040 that is capable of providing net electricity, aiming to deliver an initial design by 2024. The spherical tokamak is a variant of the tokamak design that is more compact and can support a much higher plasma pressure for a given magnetic field. It is, however, a relatively new concept and does not have the huge plasma database that we saw earlier for the conventional ITER-like tokamak. A key input to the STEP programme, therefore, is not only to learn from our participation with Europe in ITER and IFMIF donors, but also to perform experiments on a new spherical tokamak called MAST-U that is just starting to operate here in the UK. Together with advanced computer simulations and theory, and the US sister spherical tokamak NSTX upgrade that will also operate in the next few years, this will provide the scientific basis for a decision on an accelerated fusion programme via STEP.